GIS Fundamentals, Section 5, Global Navigation Satellite Systems and Coordinate Surveying. Broadly defined, there are two general ways we measure the locations of geographic features. The first uses field measurements. Field measurements may be accurate to within millimeters. The second set of location measurement techniques uses remote data collection primarily from aerial and satellite images. Coordinate positions may be obtained to within a few centimeters or inches from properly collected, carefully processed images. GNSS Basics. The Navstar Global Positioning Satellite was the first deployed and is the most widely used system. There is an operational Russian system named GLONASS that is increasingly used internationally. At the time of this writing, there are 24 operational satellites and several spares in orbit, giving complete 24-hour coverage worldwide. A third system, Galileo, is being developed by a consortium of European governments and industries with a planned total of 30 satellites in the constellation, scheduled for completion in 2018. A fourth system, the Chinese Compass Satellite Navigation System, is also under development. A full constellation of 30 positioning satellites is planned with global coverage. There is a regional system by the Indian government, IRNSS, with 7 satellites giving coverage to South Central Asia, operational in 2015. Regional systems for India and Japan are also under development. There are 3 main components or segments of any GNSS. The first is the satellite segment. This is a constellation of satellites orbiting the Earth and transmitting positioning signals. The second component of any GNSS is a control segment. This consists of the tracking, communications, data gathering, integration, analysis, and control facilities. The third part of GNSS is the user segment, the GNSS receivers. The 3 main components of any GNSS are the satellite segment, the control segment, and the user segment. The Navstar GPS includes a constellation of satellites orbiting the Earth at an altitude of approximately 20,000 kilometers. The initial system design included 21 active GPS satellites and 3 spares, distributed among 6 offset orbital planes. Every satellite orbits the Earth twice daily, and each satellite is usually above the flat horizon for 8 or more hours each day. There are 5 tracking stations in the GPS system, with a master control station in Colorado. The GLONASS system is another currently operating GNSS. GLONASS was initiated by the former Soviet Union in the early 1970s. GLONASS was designed to include 21 active satellites and 3 spares. There are 30 satellites planned for the complete Galileo constellation. Satellites are arranged in 3 orbital paths at a 54 degrees orbital inclination, with a satellite altitude near 23,600 kilometers above the Earth. This satellite constellation will provide better coverage of high northern latitudes than the U.S. Navstar GPS system to better serve Northern Europe. GNSS broadcast signals. GNSS positioning is based on radio signals broadcast by each satellite. The Navstar GPS satellites broadcast at a fundamental frequency of 10.23 MHz, or a megahertz is millions of cycles per second. GPS satellites also broadcast at other frequencies that are integer multiples or divisors of the fundamental frequency. There are two carrier signals, L1 at 1575.42 MHz and L2 at 1227.6 MHz. These carrier signals are modulated to produce two coded signals, the CA code at 1.023 MHz and the P code at 10.23 MHz. The L1 signal carries both the CA and P codes, while the L2 carries only the P code. Positions based on carrier signal measurements, L1, L2, and L5 frequencies for the Navstar GPS, and sometimes referred to as carrier phase measurements, are inherently more accurate than those based on the code signal measurements. The mathematics and physics of carrier measurement are better suited for making positional measurements. However, the added accuracy incurs a cost. Carrier measurements require more sophisticated and expensive receivers. Perhaps a greater constraint on carrier measurements is that carrier receivers must record signals for longer periods of time than CA code receivers. Each GPS satellite also broadcasts data on satellite status and location. Information includes an almanac, data used to determine the status of satellites in the GPS constellation. The broadcast also includes ephemeris data for the satellite constellation. The other GNSS systems operate in a similar manner, with base or carrier frequencies and modulated or coded signals embedded within these carriers. GLONASS, the only other fully operational GNSS in 2011, broadcasts L1 and L2 carriers similar to GPS and an additional L1, L10, and experimental G3 signal at higher and lower frequencies. Substantial effort has been directed at ensuring the Navstar, GLONASS, and Galileo systems do not interfere with each other and are as compatible as practical. Range distances. GNSS positioning is based primarily on range distances determined from the carrier and coded signals. A range distance, or range, is a distance between two objects. The range distance from the receiver to each satellite is calculated based on signal travel time from the satellite to the receiver. The range equals the speed of light times the travel time. The difference between transmission and reception times is the travel time, which is then used to calculate a range distance. A range measurement is combined with information on satellite location to define a sphere. A range measurement from a single satellite restricts the receiver to a location somewhere on the surface of a sphere centered on the satellite. Range measurements from two satellites identify two spheres, and the receiver is located on the circle defined by the intersection of the two spheres. Range measurements from three satellites define three spheres, and these three spheres will intersect at 2 points. A sequence of range measurements through time from three satellites will reveal that one of the points remains nearly stationary, while the other point moves rapidly through space. The point moves through space because the size and relative geometry of the spheres change through time as the satellites change positions. If system and receiver clocks were completely accurate, it would be possible to determine the position of a stationary receiver by taking measurements from three satellites over a short time interval. However, simultaneous measurements from four satellites are usually required to reduce receiver clock errors and to allow instantaneous position measurement with a moving receiver. Several methods are used to improve our estimates of receiver position. One common method involves collecting multiple estimates of stationary receiver location. Alternative methods for reducing positional error rely on reducing the several sources of range errors. Sources of range error. Ionospheric and atmospheric delays are major sources of GNSS positional error. The Earth is surrounded by a blanket of charged particles called the ionosphere. Range errors occur because the GNSS signal velocity is altered slightly as it passes through the ionosphere and the atmosphere. We may reduce ionospheric errors by adjusting the value used for the speed of light when calculating the range distance. Specialized dual-frequency receivers collect information on multiple GNSS signals simultaneously and use sophisticated physical models to remove most of the ionospheric errors. Dual-frequency receivers find more limited use in part because they are more expensive than code-based receivers and because they must maintain a continuous fix for a longer period of time. Finally, there are no good models for atmospheric effects. Thus, there is no analytical method to remove range errors due to atmospheric delays. Signals may reflect off objects prior to reaching the antenna. These reflected multipath signals travel a farther distance than direct GNSS signals, and so introduce an offset into GNSS positions. Multipath signals have lower power than direct signals, so some multipath signals may be screened by setting a threshold signal-to-noise ratio. Multipath signals are most commonly a problem in urban settings that have an abundance of corner reflectors, such as the sides of buildings and streets. Satellite geometry and dilution of precision. The geometry of GNSS satellite constellation is another factor that affects positional error. Range errors create an area of uncertainty perpendicular to the transmission direction of the GNSS signal. Satellite geometry is summarized in a number called the dilution of precision, or DOP. There are various kinds of DOPs, including the horizontal, HDOP, vertical, VDOP, and positional, PDOP, dilution of precision. The PDOP is most used and is the ratio of the volume of a tetrahedron created by the four most widespread observed satellites to the volume defined by the ideal tetrahedron. This ideal tetrahedron is formed by one satellite overhead and three satellites spaced at 120-degree intervals around the horizon. This constellation is assigned a PDOP of 1, and closer groupings of satellites have higher PDOPs. Lower PDOPs are better. Receivers typically provide a measurement of PDOP while data are collected, and a maximum PDOP threshold may be specified. If more precise coordinate locations are required, then the choices are to use equipment that makes more precise range measurements, and/or to collect data when DOPs are low. GNSS accuracies depend on the type of receiver, atmospheric and ionospheric conditions, the number of range measurements, the satellite constellation, and the algorithms used for position determination. Current CA code receivers typically provide accuracies between 3 and 30 meters for a single fix. Accuracies may be improved substantially to between 2 and 15 meters when multiple fixes are averaged. The longer the data collection time, the greater the accuracy. Accuracies when using carrier phase or similar receivers are much higher, on the order of a few centimeters. Differential correction. An alternative method, known as differential positioning, employs two or more receivers. Differential positioning measurements are used primarily to remove most of the range errors and thus greatly improve the accuracy of GNSS positional measurements. Differential GNSS positioning entails establishing a base station receiver at a known coordinate point. In differential correction, we use the known base station position to estimate the timing errors and hence range errors. Our roving receivers must be near our base station for differential correction to work. Differential correction requires the base station and roving receivers to collect data from a similar set of satellites. Post-processed differential correction, as corrections are applied after or post data collection. Post-processed differential positioning is suitable for many field digitization activities. Post-processing differential positioning has one serious limitation. Because precise positions are not known when the rover is in the field, the post-processing technologies are useless when precise navigation is required. Real-time differential positioning. An alternative GNSS correction method, known as real-time differential correction, may be appropriate when precise navigation is required. Real-time differential GNSS positioning requires a communications link between the base station and the roving receiver. Each position fix by the roving receiver is matched to the corresponding correction from the base station radio broadcast. The appropriate correction is then applied to each fix, and accurate field locations are computed in real time. WAAS, augmentation, and satellite-based corrections. The Wide Area Augmentation System, WAAS, is administered by the U.S. Federal Aviation Administration to provide accurate, dependable aircraft navigation. WAAS uses a network of ground reference stations spread across North America to correct GPS signals. Real-time, kinematic, and virtual reference stations. The highest accuracy differential correction is provided with dual frequency carrier phase positioning, often called real-time kinematic RTK GNSS. The amount of ionospheric delay is different for different frequencies. So, by comparing signals such as the GPS carriers L1 and L2, the ionospheric delays may be estimated and removed. RTK is such a powerful technology that many state governments are establishing a dense constellation of dual-frequency receivers in a virtual reference station network, or VRS. Stations are spaced in a network over some region such that a roving receiver is never more than an acceptable distance from a base. Precise point positioning. Precise point positioning, or PPP, is an alternative to differential correction. This technique uses precise satellite, clock, and orbit measurements to solve for point locations without reference to a set of base stations. The PPP requires complex calculations on long, uninterrupted observations on a satellite set for highest accuracies. It can take tens of minutes, and in extreme cases up to hours, for a solution to converge on a stable value. A caution on datums. Errors may easily be injected into GNSS data due to improper datum transformations. Optical and laser coordinate surveying. Surveying is particularly common for highly valued data, such as real estate in upscale markets. Other commonly surveyed features are power lines, fiber optic cables, and utilities. Plane surveying is horizontal surveying based on a planar or flat surface. In plane surveying, we typically assume plumb lines are perpendicular to the surface at all points in the survey. Distance and angle measurements are the primary field activities in plane surveying. Distances are measured between two survey stations which are points occupied on the ground. There are two common ways of specifying angles. The first uses the azimuth. An azimuth angle is measured in a clockwise direction, typically relative to grid or geographic north. Azimuths vary from 0 to 360 degrees. Angles may also be specified by bearings, which use a north or south reference direction and an angle amount and an east or west angle direction. The angle and direction are specified as north 71 degrees east or south 37 degrees west, for example. Many surveys are traverses, a series of connected lines that have a marked beginning and end point. Traverses typically start at a known control point or start at a point that has been referenced to a control point. A distance and angle are measured from the control point to the first survey station. Coordinate geometry, or COGO, may be used to calculate the station coordinates. A traverse may be open with a different beginning and ending point, or closed with the traverse eventually connecting back to the starting location. Coordinate geometry consists of a starting point, a station, and a list of directions, or bearings, and distances to subsequent stations. If traverse angles are provided as bearings, they are typically converted to azimuths first. Terrestrial, three-dimensional lasers are rapidly becoming common, although currently used primarily for structure analysis, may be used for GIS data entry. GNSS applications. Navigation is finding a way or route, and tracking involves noting the location of objects through time. Field digitization. Field digitization is a primary application of GNSS in GIS. GNSS data are often more accurate than data collected from the highest quality cartometric maps. GNSS is often used to directly digitize new control points. GNSS measured control points are the basis for almost all current projects that perform analytical correction of aerial imagery. GNSS significantly reduces the cost of control point collection, thereby making single or multi-photo correction a viable alternative for most organizations that collect spatial data. GNSS data collection for area features suffer from a number of unique difficulties. First, it takes considerable time to traverse an area. Second, it is impossible to walk exactly the same line and record the same coordinates when GNSS digitizing a new polygon that is adjacent to an already digitized polygon. Field digitizing accuracy and efficiency. Field GNSS collections are affected by an obstructed sky. Terrain, trees, buildings, or other objects block out portions of the sky, causing temporary interruptions in satellite reception, or forcing the GNSS receiver to estimate position from a constantly changing set of satellites. Maximum collection rates when GNSS digitizing are typically near 1 fix per second. Obstructions may increase collection intervals to several seconds or minutes. Sky obstructions reduce the efficiency of field digitization because more time is spent collecting a given number of fixes, and personnel must wait for the satellite constellation to change when satellites are too few or poorly distributed. Alternatively, they may collect fewer positions, thereby reducing positional accuracy. GNSS signals may pass through foliage when collecting data below a forest canopy, although signals become weaker as they pass through several canopy layers. Under dense canopy, the available satellite constellation may change frequently. Slightly changing the position of the GNSS antenna by raising or lowering it may result in a new constellation of visible satellites. Despite these efforts, efficiency reductions may be substantial, doubling or tripling collection times, but single fix collection times rarely take longer than a few seconds to minutes when forest canopy is the primary sky obstruction. Collection times will increase correspondingly when multiple fixes are required per feature, as when collecting 100 fixes for each point feature. Atmospheric interference is magnified at low horizon angles, substantially reducing GNSS accuracy. GNSS receivers designed for GIS data collection typically provide settings that automatically reject satellites below a specified horizon angle. The use of a range pole is perhaps the easiest, most common, and often most effective method to improve collection efficiency. A range pole is an extendable pole on which a GNSS antenna is mounted. There is often a trade-off between accuracy and efficiency during field digitization, particularly in obstructed locations. As GNSS receivers improve and can measure GPS, GLONASS, and Galileo GNSS simultaneously, efficiencies and accuracies in obstructed environments will substantially increase. We may improve the efficiency of GNSS digitization by altering PDOP and signal strength thresholds. But this often comes at the expense of decreased accuracy. Accepting higher PDOPs increases the number of fixes recorded, but at lower accuracies. Multipath signals have larger range errors. Lowering the threshold for acceptable signal strength is likely to increase positional error, as it increases the likelihood of multipath measurements. GNSS receivers specifically designed for GIS data collection may be fitted with a sensitive antenna that also reduces multipath reception. Setting the maximum acceptable PDOP higher or acceptable signal strength thresholds lower will increase efficiency of collection, but often at the cost of increased error. Rangefinder integration. Peripheral measuring devices, such as laser rangefinders, may be attached to GNSS data collectors to substantially improve field data collection. These devices typically measure distance with a laser and measure direction with a compass. Measurements are made from each occupied GNSS point to the nearby features of interest. The target coordinate calculations are often automatic because direction is measured with an integrated electronic compass. The rangefinder is pointed at the feature to be digitized. The system calculates the observer's position from the GNSS, and this position is combined with distance and angle measurements in coordinate geometry to calculate feature coordinates. The person operating the GNSS laser rangefinder may stand in one location and collect positions for several to tens of features, thereby saving substantial travel time. GNSS height measurement. GNSS are often the easiest way to measure new heights, but care must be taken to ensure heights are relative to an appropriate vertical datum. GNSS heights are typically determined as a height above an ellipsoid, or HAE, and many less expensive GPS receivers have no options to report any other height. Our standard height reference is a vertical datum and not an ellipsoid, so we must convert the HAE to an orthometric height above a datum prior to most uses. Orthometric height is calculated via the equation uppercase h equals lowercase h minus n, where lowercase h is the ellipsoidal height and n is the geoidal height. So orthometric height is the ellipsoidal height minus the geoidal height. GNSS tracking. GNSS tracking of people, vehicles, packages, or animals is an innovative and growing application of GNSS. GIS Fundamentals, Section 5, GNSS, Section Summary. GNSS is a satellite-based positioning system. It is composed of user, control, and satellite segments and allows precise position location quickly and with high accuracy. GNSS is based on range measurements. These range measurements are derived from measurements of a broadcast signal that may be either coded or uncoded. Uncoded carrier phase signals are the basis for the most precise position determination, but are of limited use for locating features due to measurement requirements. Code phase measurements are primarily used for feature collection and entry into GIS. Range measurements from multiple satellites may be combined to estimate position. GNSS positional estimates contain error due to uncertainties in satellite position, atmospheric and ionospheric interference, multipath reflectance, and poor satellite geometry. These uncertainties vary in time and space. There are a number of ways to ensure the highest accuracy when collecting GNSS data. Perhaps the greatest improvement comes from differentially correcting GNSS positions. Differential correction is based on simultaneous GNSS measurements at a known base location and at unknown field locations. Errors are calculated for each position fixed at the base station and subtracted to the field collections to improve accuracy. Accuracy may also be improved by collecting with low PDOPs, averaging multiple position fixes for each feature, avoiding multipath or low horizon signals, and using a GNSS receiver optimized for accurate GIS data collection.